So we've been working with limits for quite a while now. We've taken our first exam on limits, and we actually haven't given the formal definition of a limit yet. So we're going to do that now, and it's a really interesting mathematical idea, and it's especially for those of you that go forward in math or science, it's something that you will see again. And it turns out that if you wanted to go through and rigorously do all of calculus, meaning proving every step of the way, this is kind of the most basic tool you have. These are called your epsilon delta proofs. Okay. I will say, though, that once you've mastered epsilon delta proofs, it doesn't necessarily make finding limits any easier. It just makes the work that you do more complete. So don't feel like you were missing something in this first chapter because we hadn't covered the formal definition, because you're going to see that we'll get through this and we're going to prove some pretty basic limits, but we're not going to do very many hard limits because these epsilon delta proofs require a lot of work. Okay? Because these are so abstract, and because I'm not expecting you to have mastered this concept, I'm going to make it very clear what question will be on your exam for this section. Okay? And so we'll see that here in just a minute. So I'm going to do a number of questions, but then I'll highlight which one will be on your exam, up to the numbers. All right. So here we go. We're ready to give the formal definition of a limit. So this looks like something we've seen before. We said let f be a function defined on some open interval containing the limiting value, the place that we're going to be approaching, a. It doesn't have to be defined at a itself. In a lot of cases, functions aren't defined at the place where we're taking the limit, right? That's what we've seen. Okay. So then we say that the limit of f of x as x approaches a is L. Okay, so that's that notation. We've been using this notation all along, but if you remember, when I first gave this definition way back in section 2.2, we said if as x gets closer and closer to a, f of x gets closer and closer to L. Well, that closer and closer explanation isn't a good explanation. Okay, so now we're actually going to define this correctly. So we're going to say if for every epsilon greater than 0, there exists a delta greater than 0. If you're having a hard time writing those letters, here's an example of the delta down here. There's an example of the epsilon right there. Okay. So if for every epsilon greater than 0, there exists a delta greater than 0, so that whenever the absolute value of x minus a is less than delta, we have that the absolute value of f of x minus L may be made less than epsilon. Holy cow. This is a pretty complicated definition. So let's see if we can parse it out a little bit. So again, I'm not going for mastery right now. Okay, so what you're going to try to do is you're going to try to mimic what I do with these proofs. One thing I think that is extremely helpful in looking at these proofs is that I want you to think of absolute value as a distance. If you think about absolute value as a distance, I think it helps to explain this verbiage. The next thing I want to say is we usually use these epsilons and deltas to stand for very small quantities. So somebody hands you a small quantity, okay, an epsilon value. If you want, it might be helpful to think about this epsilon value as an error. Error allowance. Okay. We believe that the limit's going to be L, but we're willing to tolerate a certain amount of error. You don't have to get, if you think the limit is 3, you don't have to get to 3.3 exactly, but if you get to 3.001, we'll be satisfied. Okay? So that epsilon is a tolerance that you're willing to accept. It's an error tolerance. Okay? So somebody specifies, say, I want you to get within 1/1000th of the true answer. I want you to get within 1/1,000,000,000th of the true answer. Somebody specifies that error tolerance to you. Okay? You say, fine, we can get within that error tolerance, provided we get within this close of the limiting value. We plug in numbers this close to the limiting value. Okay? Let's read this expression here then. Okay? So the distance between x and the limiting value, as long as that gets smaller than the delta value, then it will force the distance between the range values and what we claim the limit is to be smaller than your error tolerance. That's how we interpret that. Okay? So again, think of these epsilons and deltas as small quantities. Okay? The epsilon is how close do you want to get to the true limit value. The delta is how close you have to get to A to ensure that you get within that range of the true limit value. Okay? Let me add. I think I said it when I wrote it, but I don't see it here now, so I didn't write it. For every epsilon greater than 0. Now you don't really need that word every, but I want to point to it right now. Okay. So now that I did that, what is the most complicated word in that definition? Every. Okay. So I said, okay, let's suppose somebody gives you an error tolerance. They say, I want you to be within 0.1 of the true answer of the limit, and you say, fine, as long as you get your a value with your x value within 0.003 of a, you'll guarantee to be within your error tolerance. We just did that for one case. What does the definition say? We have to be able to do that regardless of what error tolerance we're given, regardless of what epsilon value we're given. It has to hold for all of them that you're able to do this. Okay. So again, let's say it one more time. We think of this expression x minus a. That is the distance between the domain values and the limiting value. The values that we're plugging into the function and the value that we're supposed to be approaching. Okay. I just remembered something more. I really should write 0 is less than absolute value of x minus a, which is less than delta. I should have put a 0 in front of that. How come? Because when we take a limit, we don't actually plug in a itself for the x value. So this absolute value can't have a 0 in it, so x can't be a. Okay.